So basically, one of the major things that I've worked on at Wolfram Research since I started about a year ago is the back-end code for the EIWL API that grades the exercises that go with the book. So as an example of what they look like, in case you haven't seen it, but I'm guessing most people here have, this is how it starts out. If you want, visit this site here and try some of these out as we go. But basically, I'm going to be talking about how it works briefly, and some of the cool things you can do with the Wolfram language to basically make this type of thing possible. So anyways, you've got these exercises online that go with the book, and they're pretty easy. So this seems like a really simple problem. I was asked to write an API that could take basically user programs, compare that to an answer key, and decide whether or not they got the right answer. So compute 1 plus 2 plus 3, easy, got it correct. It marks it when it's wrong as well. So I'm doing pretty good so far. So one of the questions you have to ask is, how do you decide when a program is correct, given some answer key? You could look at the actual structure of the code, what they've written. Is the program identical to the one in the answer key? So in that first example, it asks you to compute 1 plus 2 plus 3. If that's your definition of equivalence, then only 1 plus 2 plus 3 will give you the right answer. If you do it backwards, not going to work. Another way of determining equivalence, which is probably the intuitive way people would think of doing this, is you just evaluate code and see what you get for the output. Obviously, that makes sense here. It'll allow things that are equal. It makes sense for arithmetic. But there are some things you need to be concerned about when using that approach, especially when you're running a publicly available API in the cloud. So one of the questions is, you have to somewhat arbitrarily decide what should be considered correct and what shouldn't be. There's a lot of gray area here. So 1 plus 2 plus 3 gives the same output as echo of 1 plus 2 plus 3. Are they the same program, though? Do they do the same thing? So that's one of the things you have to keep in mind. Obviously, the next one, those are two very, very different expressions, yet they produce the same output. Just to make sure you guys believe me. There's other things you have to worry about. What if somebody submits their program for that first exercise, delete all the important files that run the API? Do you want to run that? How do you know that it's OK to run? Then you have things like random values. That's where things get pretty tricky. You can seed the random number generator. That's one way of addressing that, but that doesn't address all cases, because should these be considered equivalent? If you take 10 random integers up to 10, and then you do the same thing, but then reverse them, is that an equivalent program? They're being sampled from the same distribution, but you're going to get different answers. But they're just as good, right, in some sense? So yeah, it is a hard problem. But the good news is it mostly works if you throw a whole lot of stuff at it. Here's an example of some of the things where it does handle those types of problems I was talking about. So for example, that echo there in that pie chart, none of that will ever show up in the actual output, but it's generating a side effect, which alters the behavior of the program. The third one also has that, but it's not actually evaluated because of the hold. So that does generate the same thing. I used a bit more complicated example on the next one, but you probably don't want me to go through each of them to see why they're correct or incorrect, but the fun example is the second to last one. And I think it's pretty neat that it can figure that out. So how does it work? That's what I want to talk about. I believe I can do that. Okay. Okay, so the two types of equivalence that I already mentioned, basically the simple and straightforward methods are looking at the input of or the original form of the code, I should say, and the other is just evaluate them and see if they get the same thing. There's a lot more you can do here, though. As an example that most people are probably familiar with as another form of equivalence, the testing equality and for mathematical values. So if you do equals instead of same Q, for example, that's totally different definition of equivalence, and that's doing all kinds of neat stuff to figure that out. And that's kind of what this is doing. It's sort of basically coming up with an equals function for arbitrary programs, very small programs for these exercises, which is why this is actually even feasible. So next one is equivalence by definition. The symbol red, for example, that's equivalent to RGB color 100. How do we know? Because we can just look. So we know when we evaluate that, that's going to be equivalent. They're going to evaluate the same thing. So you would think, the sizing kind of threw off the alignment here. And I don't know how to use a Mac, so I'm just going to leave it that way. But these are otherwise the same expression, except for the red and the RGB color. So what happens when I evaluate that, do you think? Or when I compare them? What do you think? They're the same thing, right? No, they're not. And I just looped it around again. But here's why, and this actually shows up a lot. This is one of those types of problems where at first you look at it and be like, oh, just evaluate it. You get the same result, no big deal. You spend 2 or 3 days working on this and you're done. Deploy it, move on to the next thing. But no, the more you look at it, the weirder it gets and the more difficult it gets. So when you're dealing with these dynamic boxes, for example, or dynamic modules with their own local variables, you've got that in it. It's otherwise the exact same expression, except you've got these local variables that get named differently. So you can't just, you can't run same queue on either the input in this case because of that RGB color and red difference, and you can't do it on the output, but they are the same. I think everyone here would agree that they're doing the same thing in any way that we would care about. So what we can do in this example, because there's only one difference here, and we have a definition saying that these are exactly the same, just replace it. Easy enough. And this is kind of the fundamental part of how the grading system works. I would say about half of them are just evaluate it and see if they're the same. So the ones that like 1 + 2 + 3, it's just going to evaluate it, doesn't care. It's going to do it the simple way. But there are so many examples in those exercises. We have things like dynamic modules, you have things like cloud deploy, and things that you're just generally not going to be able to run in an API in the cloud, like arbitrarily. So it takes a lot of magic, I guess. So coming up with these rules, for example, red and RGB color, that's an easy one. Sorry, my computer keeps not moving. Did I just go back a page? Nope, that's a whole cell opener. I did not know that. Okay. So one of the things to make this easier is automate as much as possible. Discover these rules without having to manually figure out all these different things. Like, you don't have to look for all the colors. You just get the list of all the names. You make sure they're not read protected, because otherwise you're not going to be able to look at the definition anyway, and it's going to throw errors at you. And you just look for rules. In this example, I'm just looking for RGB color. You could do this for anything else, really. In fact, you probably do want to make it more general. But this is an example of how you can get all the rules for the named colors. And now I can use this set of rules to eliminate any instance of these named colors in any expression. And they show up a lot in these EIWL exercises. So what that's doing is, however many there are there, like maybe 20 or so, that's basically reducing the size of the language by about 20 symbols, which that's a very, very small slice of what's there. But the more you can do that, with the smaller the languages, the smaller the set of patterns you have to consider for these types of rules you want to do. So trying to find like these examples where you can knock out a whole bunch of symbols at once, that really helps you out in the long run. And obviously that is going to work for that example from earlier. You don't actually have to evaluate it. There are also methods where you could evaluate them and then renormalize the variables test, but just replacing the red, I think, is easier for this one. So equivalence by definition, that's just quite literally look at the definition of symbols and see what they're the same as, and just replace them as necessary. And in fact, when you get the definition of symbols, like with own values or down values, things like that, you're getting a list of replacement rules, because that's how the language fundamentally works. It's a term rewriting system. You've got basically a set of rules that tells you how to transform expressions, and it does its thing. Fortunately, you can also override much of that. All right, so propositional equivalence. So there are other things, in fact, the vast majority of the transformations that are useful for this, that you're not going to be able to discover through definition. There's a lot of kernel functions, for example, that you can't just check to see if they're doing the same thing. So for example, any range can be expressed as a table. So however you have the argument set up. And this is assuming that you're not interested in like range of a string, for example, because that's technically a valid expression, but it's going to generate a message, and it's not useful for anything. So yeah, those are the same. And that's how we can express that equivalence as a replacement rule. So taking any range with its arguments, and like I said, this is assuming you don't care about ridiculous forms of it, like range of like 300 arguments or whatever. Because obviously that's not very useful. No one's going to do it. So here we have another example where the inputs are different, and because of those random integers in there, the outputs would end up being different too. But just using this rule here, that's an example of the different outputs, but you don't even have to evaluate it. You just use your rule, which, I mean, doesn't seem like you can get very far with like one or two at a time, and this is going backwards again. Help, I'm not good at computer. Okay, so yeah. So table and range are two extremely common functions in the language. And like I was mentioning before, being able to reduce the size of the language, not just in the number of symbols you're dealing with, but the number of patterns, in a sense, that you would want to deal with, even though they're pretty much all infinite for the ones we're interested in. But going the other way around, instead of converting ranges to tables, would we be interested in converting tables to ranges? We can for some of them, but not all of them. Like this table here, how would you generate that with range? You just can't. So table, in a sense, is a larger class of possible expressions than range. So all ranges can be mapped into tables, but not the other way around. And that's an important thing to keep in mind when you're coming up with these rules. So here's an example of an ugly rule that does what I just said, which I wouldn't recommend going that direction. And you could also have done the same thing with the RGB color in red. But think about that. That doesn't go the other way as easily. So if we were looking at patterns like this, obviously those aren't all going to be able to map to red. So with what I was saying before about how one represents a larger class of expressions than the other, the same is true within the types of tables you might see, where you could have these iterative forms where you just have your two integers. So it's your minimum value and then your maximum value that it goes to. But those can also be represented by this class of patterns as well, just by that last integer being a 1. But not all these 4-argument lists here can be represented by the 3-argument form. So it's defining a gradient that you really want to follow, where you're mapping in the direction where things will always fit. So when you're considering these replacement rules, you also have to make sure you don't do things like create infinite loops. So if you had one rule in there where it's mapping these symbol integer to these 3 integers down here, and you had another one going the other way, you're not going to get very far with trying to reduce expressions with that. So, and this is the rule that does what I just mentioned. Putting that 1 there will eliminate all tables of this form. You don't have to worry about that pattern anymore. So what this is doing is, as you come up with these rules where you're mapping things into these, I guess, larger equivalence classes, you're basically following a gradient. And the idea is, as you keep transforming these expressions, if they're equivalent, without having to evaluate them, if you have a nice set of rules, they should converge at some point, because they're tracing these transformations, which by themselves represent equivalence relations. And if you're preserving the expression as you go, and they do eventually converge, then you know that their original forms should also be equivalent. But there are some other issues. So for example, here's another one where you can take a symbol and an integer of a table and also map it to that 4-argument list iterator. So that's also eliminating all these forms of tables here that you don't have to worry about anymore. But one of the things you have to keep in mind, very significant that you make sure you match your patterns to the appropriate head. So if I didn't have integer here, I could potentially grab a list, which that represents something totally different and is a totally valid thing to do. So here's where things get difficult. This one here, this n, that's not going to match this when it's in this held form here, because that's not an integer. So the pattern matcher is not going to see that as an integer, even though I know it's going to be an integer during evaluation. Pattern matcher doesn't know that. So I could come up with some really big, complicated-looking rules where it's looking for nested tables and things like that, and things start running really slow if you start taking that approach. And it's pretty hard to avoid this type of thing running slow to begin with, but doing that would just be a disaster. And that's no good. We were unable to eliminate that two-argument form of this iterator, even though we have the rule to do so. It just can't recognize it. This is what we want to see. That's the desired goal. That's what I call the canonical form of this expression, having these 4 arguments per iterator here, assuming they're actual numeric values and not a list. So I'm hesitant to call it a type system because it doesn't do all the things one would normally associate with a type system. So it's not going to do like all the neat static analysis stuff. It's basically all it does is it looks for expected patterns. So it's basically a way of propagating patterns lower into the expression without evaluating it to basically assign what you know that it's going to match. And that's all in this package here. And with any luck, because I'm not on a branch that I think is stable. Okay, yeah, it did work. Neat. So it looks different. I did that to basically save myself time in the long run, because these are big, ugly things otherwise. But this handles that issue that was in the way. So for example, actually the intermediate form up here is the one that would have had the example. But I'm going to grab that one. So there we go. It's currently not in a form that you would usually want, because those aren't symbols anymore. Those are that kind of type wrapper where it's really just neat. All right, well, I lost that out of the table, but you believe me, right? Reload that. Oh, and this is the thing that I lost before I didn't want to. Oh, no. I think it should be fine, though. Yeah. That's for other stuff. But this is a way to take these three expressions, which are very different from each other. In this case, maybe it's not the best example, because these would all evaluate to the same thing. That's all deterministic here. Probably should have put random numbers in there or something. But just to show you that without evaluating it, I can determine that they're the same thing. And that's type system. And I should rename it, because it's really not a type system. Because this is just the expected pattern that I care about. It's not integer as a type, because you can also have a form where it has, blank sequence or blank null sequence, things like that. And that's also a valid thing. So what I was mentioning earlier about how equivalent expressions should converge at some point during these transformations, you can kind of visualize that. So you can see exactly when, for example, well, first thing it does is it normalizes these names, because if this is table J, for example, how would you compare that to the iterator with I? So this is just more box form stuff, so I don't have to try and hurt my brain reading these awful outputs. I highly recommend box forms for anything that you don't want to look at on a regular basis. So here's what we have. First thing, normalizes all the names, and actually, it kind of skipped a step, because the first thing it does is map this first outer set of iterators here to its 4-argument form. It knows automatically, sees this is an integer, it can match that one. It's immediately going to expand that as its first step. And so now it has symbols in here. It still can't do anything with this one. Doesn't know yet what that's going to be. But now looking at this one here, and it sees that these are all integers over here, it's like, OK, these are integer iterators. I know that this one here, and I should have made the box form preserve the numbers, but oh well. Now at this point, it knows, because these are integers, this is going to be an integer, which replaces all occurrences of itself with that integer. So you can kind of see how this data flow occurs with this trace here. So this sends this integer pattern down into the nested table. And now in the next step, the rules look at this and be like, OK, I have a symbol here. Now I know this isn't a list. Now I know it's an integer, even though it's not your usual integer pattern. It's this wrapper here. But you can still use these set of rules written as you normally would, and it'll convert them to do this. And then you can expand all these out into their canonical forms, even if you have these nested symbol patterns. Here's another example where, again, I'm using things that would evaluate to the same thing anyway, but I just like tables. So obviously, those are all different from each other while they're held before they're evaluated. But if I gather them by their canonical form, I can see how many equivalence classes there actually are in there. And each of those classes are equivalent by this function I made that says so. So trust me on that one for now. But if I release the hold and check, that verifies it. And this is that convergence of transformations I was talking about, which I hope this 8-year-old computer can actually do this. Oh, there we go. So the terminal points here on the graph represent the original expression. So each step, like you see in this list here, represents one of these transformations for each of these expressions. So they all started out different from each other, and they followed a path through their equivalence class. So just verifying that they're path connected in this space of expressions is a way of determining that they're equivalent. Like the middle one here, you could have determined they're equivalent without fully evaluating them as well, without going with full sequence, but it's not super efficient right now. And this also corresponds with the number of groups that were equivalent by evaluating and equivalent by my function here that I promise you works. So that's kind of the bulk of how the rule system works. Just taking these transformation rules and repeatedly applying them in a specific direction to reach this canonical form for these expressions. That still doesn't get you everything, though. There's like 150 rules or so in the system, and it still doesn't always catch everything. And in fact, if you went on those EIWL exercises right now, just knowing the language a little bit, if you wanted to find things that it can't catch, it might take you 1 or 2 tries if that's what you're deliberately trying to do. It only captures like such a small subset of the language, but it works because EIWL represents a very small subset of the language. There's something like 200-something functions, I think, represented in the book, but only a few of them are used often. And you really only have to make this good enough, because this is an impossible problem, actually, in general. Yep?
So you said for simple problems that you use somehow just do evaluation.
Mm-hmm.
So if it asks for the sum of the numbers from 1 to 3, and you type in 2 times 3.
For like those arithmetic type of problems, it's earlier versions, it would actually say in section 1, for example, if you just put 6 for the first answer, now it's just going to say it's correct. There was some extra logic in there to make sure you were in the spirit of the exercise, but it's sort of been kind of more generalized, and there's less EIWL specific stuff. So the arithmetic stuff, it's just going to evaluate it, and if it gets the same answer, it's the same. But for the things that you can't evaluate, but you do want to know about the side effects, and this might not be the best name either, because this isn't just like a don't run code type of sandbox thing. This is more of a capture side effects and keep track of stuff that happens, but still evaluate. So it was originally written as a don't run bad code thing, which it's also what it does, but its main purpose is for capturing these side effects. And yeah, that is rewritten in this version, so it does more. So this is what the output of that expression is. So I can't copy stuff, apparently. That's really weird, because I haven't had any issue with that at all. Maybe it's this building. That's totally possible, right? Someone sees me about to copy and paste something, just yell at me so I don't. I'm probably going to anyway, though.
I have a question about the exercises.
Yep.
So do you make any effort to say, functions or use the operators, or basically restrict them, saying, your task is to figure out how to use these functions to compute something?
Yeah, earlier versions, it was very much focused on doing that. So there are some exercises that say use times and range or something. I don't remember off the top of my head, but there are some that say use these functions. It used to specifically require those to be marked correct. It doesn't currently do that right now. There are things that it still does that are specific to this, like if you're using functions that don't appear in the section you're in or before that, and you get it right, it's going to say you got it right using more advanced functions. And I think the intent was to eventually like generate a message saying, why don't you move on to this other section or check out introduction for programmers or that type of thing. So it's more of a feedback thing. But it does still do some of that stuff where it's looking specifically at, I guess, the structure of the book and like what comes where.
I'm also surprised that you don't also hit on it at the very beginning with, full simplify, stuff like that, to try to understand, try to force expressions into canonical form. Just because your ad hoc rules will have a better chance if things are in canonical form.
Yeah, so actually one of the things that does occur during the transformations is there's a particular batch of rules where it's looking for like mathematical expressions with like, undefined symbols and also these like typed integers, for example, and it's actually calling simplify on those when it deems safe to do so, and that actually is one of the steps it takes, but it does so on much smaller parts of the expression because it's pretty hard to keep this thing running fast. So it works for the EIWL stuff when it's really maybe 2 or 3 lines of code at most you have to deal with. But there definitely are limitations with how much I can throw onto it. There are lots of rules and lots of things I would like to add into these transformations, but they're just not worth the performance impact.
Do you do other things like just throw out expressions that have too many heads? Just some really gross measure of complexity. It's like trying to compute 1 + 2 + 3. This should not be something that calls set function. It goes off and never computed on that.
Yeah.
I mean, they're supposed to be simple. I'm just saying, you keep saying it has to be simple, right? But I can't tell as how you restrict.
It's time constrained.
It's time.
So
That helps a little bit.
yeah, it's. I don't remember what it's set at right now. I think it's probably 5 seconds or so. But if somebody wants to compute 1 + 2 + 3 in the weirdest way possible in 100 lines, if they can do that in 5 seconds, more power to them. And that's actually sounds like a lot of fun to me. So I wouldn't want to restrict that. If they can do it under the memory limits, under the time limits, go for it. Yeah, so this is the bit where so you'll notice the echo didn't actually evaluate here. It ran through this evaluation as if it did evaluate, but it stopped it, recorded the order that these things happen in, things that generate side effects, because that's significant, and then it keeps a record of that. Like the reason it has that captured separately would be like, so that wouldn't show up in the output at all. But you wouldn't want that expression to be equivalent to just range of 5, because it does do this extra stuff. And I don't know why I just typed that in, because this does exactly the same thing that I wanted to show you. But it does keep track of things like certain functions will hold their arguments, so you don't want to just pass those down, because this form here, those are just strings there, and if this function here did not have any holding attributes, whatever's left over here is going to evaluate to make sure it does propagate those evaluations correctly. This one preserves in the trace, or in what it captures, what the form was. But these aren't all the same because I had a different value for each of those, and more box form stuff to keep track of that. Because that's another big, awful thing to look at if I didn't do that. But you can see how there's quite a bit of difference here. Because this one, you don't have to keep track of what the value of I was at the time that that print would have evaluated. Because it doesn't matter, because that's just going to evaluate before print even does anything to it, because it doesn't have any holding attributes. This one, on the other hand, has to keep track of a closure that represents the relevant part of the state of the evaluation that it needs to know. Oh. And again, I had the answer to the thing that I was trying to show. This is not right. I think after I crashed, I opened the wrong one. This is a bunch of stuff that I was thinking of putting in the slides, and most of it I actually did end up doing that, so I'm just going to mention. So these are examples that I put in the early part of the slides. That's already loaded. All right, so code equivalent Q is basically, that's a thing that compares the two expressions to see if they're the same thing without actually evaluating them. But what that's really doing under the hood is the real important function of this package is that to-canonical form, where it's converting these things to their canonical representation so they can be compared. And this is just kind of the interface to that. But the whole sandbox evaluation thing lets you do some pretty neat stuff that you otherwise would never be able to do. For example, you could evaluate these to see that they reach the same thing if your computer had enough RAM, and you would survive for however many years that is. They do evaluate to the same thing someday. But this doesn't need to do that because of the canonical transformations. And likewise, it can tell that if I add 1 to the end of there, that these are different. It's still going to run to its timeout, though, because it'll try its hardest, but it's just not going to run for 1,000 years. And so this basically captures all those different types of equivalents that I was talking about. The first thing it's going to do, oh, I was just about to copy. I'm not going to do it. So this is that first type of equivalence I was talking about. The input's exactly the same, didn't need to do anything else, saw that immediately. So it basically will try to do the simplest thing possible first, and it only resorts to these more complicated methods if necessary. So this one, for example, these obviously are not going to evaluate. That's a pretty big number. I don't think I have enough RAM to do that. So the second step it would do, that's what I should have done. Number 2. So that's the second step. And only if it can't evaluate them to determine the answer, then it's going to jump into all this crazy stuff. And then you can force it, and this is all stuff that I wasn't going to put in my slides. But and here, this is actually some EIWL specific stuff, which in general you probably wouldn't care about for this kind of package, because there's a lot of visual stuff that you're asked to generate for the answers. And so for an example like this, you might not care about the inner structure of the expression because they look the same on the screen. So what it does for those types of things, specifically for EIWL, and nope, that's broken on my local version. But yeah, on the one that's running online, it'll take things like graphics boxes and things like that, and it'll actually just rasterize them if you can't figure it out, because large graphics expressions can get pretty complicated, and that would take a really long time. And yeah, so this is just stuff that last 2 pages of my slides apparently disappeared, but I think I'm just about out of time anyway. Okay, yeah, so any questions? I have questions.
So how many people have actually, how long has this book been out? I mean, this website been out?
I think it was actually announced in May, I think.
So, wow. So what's the history of the, users?
Like how many submissions and things like that?
I mean, how's the performance of the system?
There, last I looked, which was at the data, the number of submissions I think was around 120,000. And that's all, the expressions are all stored, and it actually, one of the things it does is it tries to find new rules. And it's not fully automated yet, and it's something I've been working on. I basically want it to figure out how to improve its rule system on its own, but it does search for patterns that would represent a lot of these types of things people are doing, and to see if it can kind of tailor itself for this application specifically. But yeah, there's a lot of data.
So you run into some number of things where, you can't decide. I mean, you make a decision, but,
Yeah, and
you actually can decide.
yep, that does. Yeah, I have a bunch of verification tests that they don't run at the time that the user is submitting, because I don't want to use up their 5 seconds for my self-test type of things. But afterwards on the data, it basically combs through it and looks for examples where the 2 canonical form did not find equivalent representations, but it did evaluate something equivalent. So that's something that raises a flag. That's something I need to look at because it missed something. So initially in May, it was doing a pretty poor job of finding things. But just after like a couple of weeks of getting a bunch of these exercises in with that data and just comparing these patterns and generating new rules, it became pretty robust. And I should say that with a little asterisk, because if you deliberately want to show that it doesn't work, yeah, it's really easy to deliberately fool the thing. But for the types of answers that people are entering, if they just want to solve these exercises, it does a pretty good job. I think so, at least. Well, okay.